People always ask me, what is time? And I have to tell them, you're asking the wrong question. You're asking a question that assumes time is a thing, like a river flowing past you or a clock ticking on the wall. But that's not what time is at all. Time isn't real in the way you think it's real. It's not some absolute background against which the universe plays out its drama. It's something much stranger, much more interesting. And once you see what's actually happening, you'll never look at a clock the same way again. Let me start with something simple. You look at your watch and it says 3 o'clock. What does that mean? Well, you say it means that time has reached the position of 3 o'clock, as if time is marching forward on its own. But that's not what's happening. What's actually happening is that the little gears in your watch have turned a certain number of times, and you've agreed with everyone else that when those gears reach a particular configuration, you'll call it 3 o'clock. The watch isn't measuring time. The watch is just changing, and you're comparing its change to other changes happening around you. Now here's where it gets interesting. Every clock in the universe, whether it's a fancy atomic clock or the rotation of the Earth or the decay of a radioactive atom, is really just a physical process happening. When we say we're measuring time, what we're actually doing is comparing one physical process to another physical process. We're saying how many times did this thing happen while that thing was happening. That's all. There's no separate thing called time that we're measuring. We're just counting changes and comparing them. Think about it this way. Imagine you're in a room with no windows, no clock, nothing. How would you know time is passing? You might say, well, I get hungry, I get tired, my beard grows. But notice what you're doing. You're not detecting time directly. You're detecting changes in yourself, changes in physical systems. Your stomach empties, your cells burn energy, your hair follicles produce keratin. These are all physical processes. You're comparing these processes to each other and calling that time. So what is time then? Time is a way of talking about change. It's a way of ordering events, of saying this happened, then that happened. But the deep question is there really a universal now that applies everywhere in the universe? Is there some cosmic clock that tells us what's happening right now on Mars, right now in the Andromeda galaxy, right now everywhere? And the answer, which shook physics to its core, is no, there isn't. Einstein figured this out, and it's probably the most mind-bending thing he ever discovered, even more strange than relativity itself. He realized that simultaneity, the idea that two events happen at the same time, is not absolute. It depends on who's watching. If you're standing still and I'm moving past you very fast, we will disagree about whether two distant events happened at the same time, not because one of us made a mistake, but because the very notion of at the same time doesn't have a single answer. It depends on your motion. Let me give you an example. Suppose there are two events. A firecracker goes off on Mars and a bell rings on Jupiter. You're sitting here on Earth, and from your perspective, watching very carefully with the best equipment, you determine that these two things happened at exactly the same moment, simultaneous. Now your friend is in a spaceship flying past Earth at, say, half the speed of light. She looks at the same two events, the firecracker on Mars and the bell on Jupiter, with equally good equipment, and she finds that they did not happen at the same time. Maybe the firecracker went off first, then a little later the bell rang. Who's right? You both are. There is no fact of the matter about which event really happened first. The ordering of events that are separated in space depends on your motion through space. This is not some small effect we can ignore. It's fundamental. It means the entire universe doesn't have a single present moment. My now and your now, if we're in relative motion, slice through the universe at different angles, picking out different sets of events as simultaneous. The block universe, some people call it. All of time, past, present, and future, just exists, laid out like a landscape, and what we call now is just where we happen to be looking, a particular slice through this four-dimensional space-time. Now you might say, wait, that's crazy. I experience time flowing. I remember the past, I don't remember the future, things change, I age, the universe is clearly evolving from past to future. And you're absolutely right to feel that way. But here's the thing, that feeling, that sense of time flowing, is itself a physical process happening in your brain. Your brain is a machine that records configurations, that builds memories, that compares the current state to previous states. The sensation of time passing is a result of the way your neurons fire, the way information gets encoded in your brain structure. The arrow of time, the fact that we remember yesterday but not tomorrow, the fact that eggs break but don't unbreak, that coffee cools but doesn't spontaneously heat up, all of that comes from something called entropy. Entropy is a measure of disorder, of how many ways you can rearrange the microscopic pieces of a system while it still looks the same macroscopically. A broken egg has high entropy because there are lots of ways to arrange the pieces of shell and yolk and white to still look like a broken egg. An unbroken egg has low entropy because there are very few arrangements that give you a nice intact egg. The second law of thermodynamics says that entropy tends to increase. Systems tend to go from ordered to disordered, and this gives us the arrow of time. The reason we remember the past is because the past was more ordered. Our brains are recording devices, and recording creates order, creates structure, and that structure can only persist if the overall entropy of the universe is increasing. If entropy were decreasing, we wouldn't remember anything. We wouldn't have any sense of time's direction. But here's the puzzle. The fundamental laws of physics, the equations that govern how particles move, how fields evolve, they don't care about the direction of time. If you take any solution to these equations and run it backwards, you get another perfectly valid solution. The laws are time symmetric. An electron moving forward in time is indistinguishable from a positron moving backward in time. At the microscopic level, time doesn't have a direction, so where does the arrow come from? It comes from the initial conditions of the universe. The Big Bang started the universe in an incredibly low entropy state, incredibly ordered, and ever since then, the universe has been spreading out, getting more disordered, and that increase in entropy is what gives us the arrow of time. Time's arrow isn't built into the laws. It's built into the history, into the fact that the universe started in a special configuration. Now let's talk about what time really is in the equations. In Newton's physics, time was absolute. There was a universal time coordinate, t, that marched forward uniformly everywhere. Everyone agreed on what time it was. But Einstein showed that's wrong. In special relativity, time and space get mixed together. What you call time and what you call space depends on how you're moving. If we're in relative motion, we won't agree on how much time has passed or how much space separates two events. We have to talk about spacetime, a four-dimensional thing where time is just one dimension among four. In general relativity, it gets even stranger. Gravity is the curvature of spacetime. A massive object like the Earth bends spacetime around it, and that bending affects the flow of time. Time runs slower in a gravitational field. If you're standing at the bottom of a mountain and I'm at the top, your watch ticks slower than mine because you're deeper in the Earth's gravitational well. It's a tiny effect for a mountain, but it's measurable, and GPS satellites have to correct for it or they'd give you the wrong position. Near a black hole, time slows down enormously. If you were to fall toward a black hole while I watched from a safe distance, I would see your clock ticking slower and slower as you approach the event horizon. From my perspective, you'd take forever to reach it, frozen in time. But from your perspective, you'd sail right through in finite time, nothing special happening at the horizon itself, though you'd be torn apart by tidal forces soon after. Two different descriptions of the same events, both correct because time is not absolute. Now here's where it gets really wild. In quantum mechanics, we talk about the wave function, which describes the probabilities of finding a particle in different states. The wave function evolves according to the Schrödinger equation, and that equation has time in it. But the wave function describes all possible outcomes, all possible configurations of the system. Before you measure, the particle is in a superposition, it's in many states at once. And here's the thing, the wave function doesn't care about our perception of now, it just evolves according to the equation. Some physicists have tried to formulate quantum mechanics without time, or with time emerging from something more fundamental. The Wheeler-DeWitt equation, for example, describes the wave function of the entire universe, and it has no time in it at all. It's a static equation. The whole universe, all of its history, is just described by this timeless wave function. Time, in that picture, is something that emerges when you look at correlations between different parts of the wave function, between different subsystems. It's not fundamental. Carlo Rovelli, a physicist working on quantum gravity, has this beautiful way of putting it. He says, time doesn't exist at the fundamental level. What exists is change, things happening in relation to other things. We build clocks, we compare processes, and we call that time. But at the deepest level, there's no universal time variable. There are just quantum fields and their configurations and the relationships between them. Now you might wonder, if time isn't real, if it's just a bookkeeping device, does that mean nothing really happens? Does it mean we're just static, frozen in some eternal now? And the answer is no, not at all. Things happen. The universe is full of change, full of events, but the change isn't happening in time. The change is what we call time. Time is the change. Think about a movie. When you watch a movie, you see things happening, characters moving, plot unfolding, but the movie itself is just a reel of film, a series of static images. The images don't move. What moves is your perception, the projector showing one frame after another. The movie exists all at once, but you experience it sequentially. Space-time is a bit like that. All the events exist, laid out in this four-dimensional structure, and our consciousness, our perception, moves through it, experiencing one moment after another. But that's us. That's our brain's way of processing information, not a fundamental feature of reality. Let me tell you what I think is the most important thing to understand about all this. Physics is about finding patterns, finding relationships, finding what's invariant. We used to think time was invariant, the same for everyone. Then we found out it wasn't. We thought simultaneity was absolute. It's not. We keep peeling back layers, finding that things we thought were fundamental are actually emergent. They arise from something deeper. What's fundamental, as far as we can tell, are the relationships between events. This event causes that event. These two processes are correlated. Energy is conserved. Momentum is conserved. These are the real facts, the things that don't depend on your perspective, on your coordinate system, on how you choose to slice up space-time into space and time. Time, as we experience it, is a useful concept. It helps us organize our thoughts, predict the future, understand cause and effect. But it's not written into the fabric of reality in the way we naively think. It's an approximation, a way of talking about the universe that works well in our everyday lives, but breaks down when we look closely, when we move very fast, when we get near black holes, when we try to understand quantum gravity. And here's the beautiful thing. Once you realize this, you start to see the universe differently. You stop thinking of yourself as moving through time like a boat on a river. You start thinking of yourself as a pattern, a structure in space-time, a four-dimensional object that exists all at once from birth to death. Your entire life is a kind of static sculpture in space-time, a world line, and your consciousness is just experiencing different cross-sections of that sculpture moment by moment. Does that mean free will is an illusion? Does it mean the future is already determined? These are tricky questions, and I don't have all the answers. Determinism is a separate issue from the nature of time. Even in a block universe where all events exist, the question of whether those events are determined by earlier events or whether there's genuine randomness is still open. Quantum mechanics suggests there's randomness, that the wave function only gives probabilities, and the outcome of a measurement is not predetermined. So even if all of space-time exists together, it may not be the case that the future is fixed. What I can tell you is this: the more we learn about the universe, the stranger it gets, and the more we realize that our intuitions, our everyday experiences, are not reliable guides to how things really work. Time seems so obvious, so fundamental. We feel it passing, we see clocks ticking, we age. But underneath that, at the level of the laws of physics, time is not what we think it is. It's a coordinate, a label, a way of organizing events. It's not an absolute flowing river. It's not a universal now. It's something that emerges from the relationships between physical processes. And to me, that's not disappointing. It's liberating. It means the universe is far richer, far more subtle than we imagined. It means there's always more to discover, more layers to peel back, more mysteries to explore. We thought we understood time, and then Einstein came along and showed us we didn't. We thought we understood causality, and then quantum mechanics came along and showed us we didn't. Who knows what we'll discover next? So when someone asks me, is time real? I say, define real. If you mean, is there a thing called time that flows independently of everything else? Then no, time isn't real. But if you mean, do things change? Do events happen? Do we have a past and a future? Then yes, of course. Time is real in the sense that change is real, that the universe is not static. But the nature of that change, the structure of space-time, the relationship between past, present, and future, those are far stranger than our everyday intuition suggests. The job of physics is to figure out what's actually happening, to strip away the illusions, the convenient fictions, the approximations, and get to the underlying reality. And the underlying reality of time is that it's not a thing. It's a relationship. It's a way of talking about how different parts of the universe are correlated, how events influence each other, how change propagates through the cosmos. That's what's actually happening. Not some mysterious flowing river of time, but a four-dimensional space-time where all events exist, related to each other by the laws of physics, and our consciousness picks out a particular path through that space-time, experiencing it moment by moment, building memories, creating the sensation of now. That's the real story of time. It's not what you thought it was, and that makes it all the more fascinating.